Welcome to our expert course. In this video, we will break down the essential artificial intelligence concepts every developer must understand before integrating Spring AI into their Java applications. We assume zero prior knowledge, so let's get started on your AI engineering journey. Welcome to our training video on the core AI concepts you must know before using Spring AI. Spring AI is an amazing project designed to make building applications with artificial intelligence easy, especially if you already use the Spring framework. Think of Spring AI as a universal adapter for AI services. Its main purpose is to give Java developers a familiar, consistent experience when interacting with complex AI models, like those from OpenAI or Google. This consistency is crucial because it means your code is portable. You can switch the powerful AI model behind your application simply by changing a configuration line, avoiding being locked into a single vendor. Spring AI handles the difficult parts of sending requests and processing responses, letting you focus on your application's specific features. It provides foundational components for things like chatting, generating numerical representations of text called embeddings, and giving your AI external knowledge through retrieval augmented generation, known as RAG. Understanding these core concepts is your first step to harnessing the power of AI in your enterprise Java applications. We will start with the fundamental building block, the model itself. This diagram shows how Spring AI simplifies talking to different AI providers using a single, consistent approach. On the left, we have your main Spring AI application. This application talks only to the Spring AI abstraction layer, represented by the green block. This abstraction layer acts as a translator or mediator. Notice how the abstraction layer can connect to multiple different AI services, such as OpenAI, Anthropic, or even a local model like Ollama. For developers, this means the application code remains the same, even if the actual AI brain changes, which is the definition of portability. Spring AI coordinates the interaction with these AI providers and models, handling the underlying complexity of each specific API. This layer is key to simplifying AI integration, turning complex web API calls into simple Spring component method calls. It's the foundation that allows Java developers to integrate AI features quickly, without needing to wrestle with technical details. Now that we know Spring AI is the universal adapter, let's understand the brain it connects to, the AI model. An AI model is essentially a sophisticated algorithm that learns from huge amounts of data. It takes input, like a question or an image, and generates an output, such as an answer or a new picture. Spring AI categorizes these models by what they do. The most common type is the chat model, often referred to as a large language model or LLM. Chat models are what you use when you ask a chatbot a question. They take text in and give text back out. Another critical type is the embedding model. Instead of text, these output a list of numbers, called a vector, that captures the meaning of your input text. This is fundamental for advanced features like searching for meaning, which we will discuss later. Models today are usually pre-trained, meaning they are ready to use out of the box without requiring you to have a deep machine learning background. Developers use the core abstraction called chat model to interact with these systems. This diagram illustrates the main types of AI models supported by Spring AI, all stemming from the general concept of an AI model or LLM. The chat model is used for conversation, taking text input and returning text output. The embedding model is different, converting text into a numerical vector, which is a key concept we will explore further, as it allows machines to understand meaning mathematically. We also have specialized models, like the image model, which can process visual inputs and generate text or new images, and the audio model for tasks like converting speech to text, known as transcription. Spring AI provides abstractions like chat model and embedding model to interact seamlessly with all these different specialized AI brains. Remember that choosing the right model type depends entirely on your specific application use case. If the model is the brain, the prompt is the instruction you give it. A prompt is more than just a question. It's a guide for the AI. For the best results, your prompt needs 4 components: clear instructions about the task, any necessary external context, the direct user input, your question, and an output indicator specifying the desired format, such as asking for JSON. Crucially, many AI models support a system prompt. This special message defines the AI's role. For example, you are a professional historian, and sets the behavioral framework for the entire conversation, ensuring consistency. Since developers often need to send similar instructions repeatedly, Spring AI provides prompt templates. These are reusable text structures with placeholders, like topic, that are filled with real data at runtime, making your prompts dynamic and easy to manage. The prompt template class handles this variable substitution cleanly. This flow shows how a powerful prompt is constructed using Spring AI components. We start with the developer input, which is structured using the reusable prompt template. This template combines several critical elements. First, it includes instructions and a predefined role, which often forms the persistent system message. Second, it integrates runtime variables, like user_name or topic, which are provided dynamically by the application. Third, the template specifies the desired output format indicator, such as requiring a JSON structure. All these pieces combine to form the final prompt, which is the complete instructional message sent to the large language model. Using templates ensures that every time you call the AI, it receives a well-formed, specific, and effective set of instructions, leading to more predictable and higher quality results. Next, we need to understand tokens, which are essentially the currency and the basic building blocks of language that the AI model understands. When you input a word, the AI breaks it down into tokens. For example, the phrase "Hello Java" might be split into 3 tokens: hello, hello, and Java. Tokens are important for 2 main reasons. First, they determine the cost of using paid AI services. The more tokens you send or receive, the more you are charged. Second, tokens define the context window, which is the absolute maximum size of the conversation history and prompt the AI can look at during a single interaction. If your prompt and history exceed this limit, the model cannot process the request. Developers control output size using options like max tokens, which limits the AI's generated response to prevent large, costly, or unwieldy outputs. Mastering tokens is key to efficient and cost-effective AI development. This diagram illustrates the role of tokens and the limits they impose. When input text, such as your prompt, enters the system, a component called the tokenizer breaks it down into individual units: token 1, token 2, and so on. These are counted up to form the total tokens, which is the critical metric. The total tokens number directly affects 2 major constraints: the usage cost for commercial models, and whether the input fits within the fixed size of the LLM context window. The context window is the maximum size for the entire interaction, both the prompt you send and the reply you get. Developers need to manage this to ensure the AI has enough information without exceeding its memory limit. Spring AI allows you to control this explicitly using options to limit input and output tokens, helping you keep costs predictable and performance optimal. When an AI model generates a reply, it usually comes back as a simple text string, even if you ask it to output JSON. While this string might look correct, converting it reliably into a usable data structure for your Java application is tricky. This is where structured output comes in. This concept forces the AI to produce an output that strictly matches a predetermined format, usually defined by a JSON schema. Spring AI makes this easy using utilities like the bean output converter. You simply define a Java class, and the converter automatically generates the necessary JSON schema. This schema is then passed to the AI model as part of a detailed prompt, instructing it precisely what structure to follow. This approach is crucial for achieving type safety. It eliminates the risk of missing required data fields or incorrect formatting, which makes integrating AI responses into your application logic reliable and robust. Many major models now offer dedicated JSON modes to guarantee valid output. This sequence diagram illustrates the robust process of using structured output in a Spring AI application. It starts with the developer defining the required Java object, such as a class for a movie recommendation. Spring AI, specifically the bean output converter, takes this object and automatically generates a matching JSON schema. This schema is then sent to the AI model, along with the user's prompt, providing strict instructions on the required output structure. The AI model processes the request and returns a valid JSON string, guaranteed to adhere to the schema. Finally, the Spring AI converter takes this string and performs the critical task of converting it into a type-safe Java object instance. This structured object is then used seamlessly by your main application, allowing for reliable data integration and eliminating messy string parsing. This method is essential for production-ready intelligent applications. We learned earlier about embedding models, which output numerical vectors. These vectors are called embeddings. Imagine taking a piece of text and converting its entire meaning into a long list of floating point numbers. This numerical array captures the relationships between concepts. This means that if 2 pieces of text, like teeth cleaning and dentistry, have very similar embeddings, they are considered semantically close, even if they don't share keywords. This capability enables similarity search, which is simply comparing the numerical distance between 2 vectors to determine how similar their underlying meaning is. To manage and quickly search through millions of these numerical vectors, we use a specialized database called a vector store. Spring AI supports many vector store providers like PostgreSQL's pgvector, Milvus, and Pinecone. Embeddings are fundamental for building applications that truly understand the context and meaning of user queries. This diagram shows the process of turning text into a searchable numerical format. Input text, for example, the query teeth cleaning, is passed to the embedding model. This model outputs a numerical vector, which represents the meaning of the text. This vector is then stored in a specialized database, the vector store. When a user query comes in, it is also converted into a query vector. The vector store performs a similarity search by comparing the numerical distance between the query vector and all stored vectors. If the query vector is numerically close to a stored vector representing the concept dentistry, the similarity search result returns that related document. This powerful mechanism allows your applications to match concepts based on semantic meaning, overcoming the limitations of keyword-based search. RAG, which stands for Retrieval Augmented Generation, is one of the most important patterns for enterprise AI development. LLMs are smart, but they are not trained on your company's latest documents or private data. The RAG pattern solves this by giving the AI access to external knowledge. Here is how it works. When a user asks a question, the system first retrieves highly relevant documents from your vector store using the semantic search we just discussed. This is the retrieval step. Then, those retrieved documents are injected or stuffed into the prompt, giving the LLM the factual context it needs before it generates an answer. This augmented prompt is then sent to the chat model, which generates a response based on the new, up-to-date facts provided in the prompt. This process is essential for ensuring the AI's answers are accurate, grounded in your data, and less prone to making up false information, a problem known as hallucination. Spring AI handles this complex workflow efficiently, using the question-answer advisor. Our final core concepts are tool calling and multimodality. Tool calling, also known as function calling, gives the AI the ability to interact with your application's real-world services. For instance, if a user asks, "What is the weather like in Boston?" the AI realizes it needs to call a weather API. The crucial thing to understand is that the LLM itself does not run the function. It simply generates a structured JSON response containing the function's name, like getWeather, and the arguments, like location, Boston. Your Spring AI application receives this JSON, executes your actual Java function, and sends the result back to the LLM, which then generates the final, natural language answer. This requires developers to expose their functions as tools with clear descriptions. Separately, multimodality means the AI can handle mixed inputs, such as text combined with an image, audio, or a PDF document all at once. Spring AI supports this by allowing developers to include media objects, enabling complex requests like asking the model to summarize a PDF document. This sequence illustrates the powerful concept of tool calling, combined with multimodal input. When the user sends a prompt that requires a real-world action, like book me a flight, the LLM examines the request and the available tools. The LLM reasons that a tool is needed and sends a structured tool call request in JSON format, specifying the function name and arguments, back to the Spring AI application. The application executes its internal business logic, such as calling a booking service. It sends the tool result back to the LLM. The LLM uses this result to formulate the final answer in natural language for the user. Below this, we see the concept of multimodality. The user sends a question along with a video media file. The LLM processes both types of data simultaneously to produce a relevant text description. These capabilities extend the AI's usefulness far beyond simple chat.